Welcome back to the series of lectures on the many electron atoms for the Department of Chemistry, University of Lagos. In the last video, we talked about the orbital approximation, and then we came over where it says that each electron occupies its own atomic orbital that bears a close resemblance to one of the hydrogen-like orbitals. Okay, and helium, we could express it as 1s2, but lithium, we couldn't express it as 1s3. So before we move on to the electronic configuration of lithium, we'll talk about spin and the Pauli Exclusion Principle. The spin is a quantum number derived from the Dirac-Schrödinger equation. It is an intrinsic angular momentum of the electron that is independent of the orbital angular momentum L, and it actually brought the total number of quantum numbers to 4, n, l, m sub l, where n is the principal quantum number that governs the size of the orbital and its energy. L is the azimuthal or the orbital quantum number. The value is restricted by the principal quantum number L. The magnetic quantum number governs the orientation of the azimuthal quantum number, so it goes from L to 0 through 0 to minus L in integral steps. And then the spin is half, and its orientation number, the ms, is a positive half or negative half. According to Pauli's exclusion principle, which was also based on experiments relating to spin, no two electrons can have the same 4 quantum numbers. Or, if we have to say it in another way, no more than 2 electrons may occupy any given orbital, and if 2 occupy, their spins must be paired. So if no 2 electrons may occupy any given orbital, if we consider the helium atom has 2 electrons, electrons 1 and electron 1 and electron 2. So the principal quantum number n, since they are both in the ground state, is 1 for the 2 of them. They are both in 1s2. S for L for S is 0. Same thing for m sub L, that's 0 and 0. Then it means that the spin value must be different. So the fact that the spin values, one of them is half, the other is negative half, that means that their spins are paired. So when we say that the spins are paired, it means that one of them has a positive half and the other one has negative half. And the implication is that the electron is spinning in opposite direction. So a quick one, the Pauli Exclusion Principle is actually from a general statement that when the labels of any 2 identical fermions are exchanged, the total wave function changes sign. Fermions are particles with half-integral spins, and when the labels of any 2 identical bosons are exchanged, the total wave function remains the same. So I said fermions are half-integral spin, like electron has half-integral, carbon-13 has half-integral, so there's some other particles that have half-integral. Bosons, on the other hand, are all integral spins. So this particular exclusion principle applies to fermions. The effect or the consequences of this is that the S subshell, which 1s falls into, can only accommodate a maximum of 2 electrons. The P subshell can take P subshell, that's L equals 1, and ML is 1. So P has 3 orbitals, so there are a maximum of 6 electrons. D has 5 orbitals within it, so there are a maximum of 10 electrons. So the general formula for the number of electrons that can go into a subshell, we will remember a subshell is characterized by the orbital quantum number L is 2 into 2L plus 1. So whenever the as an aside, when the subshell has its maximum of that number of electrons, so S2 P6, it's said to be filled, and when it's half filled, it's said to be half filled. This is mentioned because filled subshells and shells are usually a stable configuration. From this, it means that the maximum number of electrons that can go into any shell, characterized by N, is a 2n squared. Okay, so the Pauli Exclusion Principle, what effect does it have on lithium? It may, therefore, our lithium atom with three electrons cannot be expressed as a 1s3 because of the imposition of the Pauli Exclusion Principle. And as a result, the first two electrons go into the 1s orbital. Then when the electrons are paired with the spin electrons are paired, then the third electron cannot go into the same 1s orbital. It goes into the next energy level. The next energy level has two subshells, the S and the P. The next energy level is N equals to 2s and 2p. In the hydrogen-like system, S, so this is an energy level, a sketch for energy level. So in the hydrogen-like system, the S and P orbitals are degenerate, which means they have the same energy. One other effect of electron-electron repulsion is that electrons with different angular momentum. If you recall, L, the quantum number L, characterizes the angular momentum. So S has a net zero angular momentum, and P has an angular momentum. It's the value of 2 h bar. H bar is the reduced Planck's constant. So if you recall, for hydrogen, S and P have the same energy level. However, for a multi-electron system, they are not degenerate. Which one is lower in energy? We will consider that with the penetration effect. So the one that has lower energy is the one that the electron goes into. To determine the subshell which the third electron goes into, we need to consider the penetrating orbital abilities of the orbital and shielding as a result of the repulsion between the electrons.